Good day, everyone. Thank you so much for watching this video. If you are in grade 11 doing physical sciences in South Africa, one of the topics that you need to know for is electromagnetism in the third term. And in this video, it will serve as a sort of an introduction into electromagnetism. Today, we're just going to be focusing on using the right hand rule. There's a video that I did, I think, 2 years ago on electromagnetism, and I've seen that a few people were asking questions. So I hope this will provide some clarity, right? Um, so the first thing that we need to do is to kind of define what electromagnetism is. And to do that, let's try to just break this term apart, the term electromagnetism. So you know that it's actually a combination of electro and which comes from electricity, right? And magnetism, which comes from magnets and magnetism. So it's almost like it's a composite of two words, electricity and magnetism. And that should tell you that we are actually studying the relationship between um, electricity and magnetism, right? And hence we form electromagnetism. When we talk about um, electricity, the basic definition is the flow of charge, which essentially creates current. So um, from electrons will move from here to here, and there will be a flow of charge, which meaning that you will have current if you have a typical circuit, right? And when we talk about magnetism, normally we're referring to the force. So think about a magnet that has both the north pole as well as the south pole. So this would be the north pole represented by the letter N as well as the south pole, right? And the force exerted by magnets when they repel or when they attract each other. So normally you know the north pole, if you take a magnet and you try to combine the two north poles or two south poles, they will actually repel. But then if you put the north pole and the south pole together, they will attract. And that thing, that attraction or repulsion, we call it a force, and it's described as magnetism. So you need to understand that here in electromagnetism, we are studying that relationship, right? So let's now move on to the next slide. Another important thing to understand about electromagnetism is this. An electric current creates a magnetic field. So if you have a circuit like we have here, so you see you have a circuit, so you have the positive terminal of your battery and the negative terminal of your battery. And this means that current will be flowing in this direction. So that's the direction of conventional current from the positive terminal to the negative terminal through this connecting wires over here. And if we have this, and we have the current flowing, we will actually create a magnetic field. So be aware of the fact that this is not a magnet, but the flow of this current through your conducting wire will actually create a magnetic field, right? And another important thing, but we'll talk about it more in the next video that will follow this one, right? Is that a change in magnetic field will create a flow of charge, meaning it will create current. So and the important thing is a change in magnetic field. If the magnetic field is not changing, there will be no creation of charge, or there will be no flow of charge, meaning there will be no current. So stay with me if this is a bit confusing. It's just important. An electric current, if it flows through a wire, there will be a magnetic field created in that wire, and a change in magnetic field will in turn create a flow of charge, right? Let's look at another example. So we said that a flow of charge will create a magnetic field, and this produced magnetic field will always be oriented perpendicularly to the direction of current. So if the current, maybe it's going in this way, it's flowing from up down there, up there, the magnetic field will just be perpendicularly. there will be a 90-degree angle between the magnetic field and your current. So that is something that is very important to understand, right? And it will become more clear when we talk about the right hand rule. So just take your right hand, right? Maybe hold a pen, and that pen or stick will act as your conducting wire that has current flowing in it, right? And the right hand rule will say that the magnetic field lines produced by a current carrying wire. So we assume this will be your current, and maybe your current is going up, and this is like your wire, right? They will be oriented in the direction of the curled fingers. So your fingers will represent your magnetic field lines, right? So those will be your magnetic field lines. And your thumb over here will just be pointing in the direction of your current. So that is the right hand rule. The right hand rule, say you use your right hand, your thumb points in the direction of the current. Let's say your current is moving in that way. So maybe this will be the positive terminal and this will be the negative terminal, and your conventional current is flowing from positive to negative. So it's pointing upwards. And your fingers, if you curl them, that will be the direction of your magnetic field. And you must now recognize that your magnetic field lines are in this horizontal direction, and your current is in the vertical direction, and the angle between the two is 90 degrees, meaning they are perpendicular to each other. I hope that is clear. The next thing we need to understand is some of the basic convention used to describe whether your current or magnetic field is into the page or out of the page. So if you draw this circle with an X, you're saying that your magnetic field is into the page, or even your current is into the page. And then if you draw a circle with a dot, it means that your current or your magnetic field is out of the page. So a pretty smart way to remember this would be to think of a dart, this thing here, and that board. So if you throw this dart and it's going into this board over there, you'll actually just see this end, the rear, the end, the back part of it, and it will actually look like an X because it will be moving away from you. So it will be going into the board, or if you do it into a page, it will be going into the page. But now if somebody decided to take the same dart and throw it towards you, it's moving towards you, you'll only see this part there, the dot. So it's moving out of the page. So when you draw your magnetic field on your page and you draw the X, the assumption is that there you see the magnetic field is going to the page, here it's coming out of the page, right? Wonderful. So let us look at an example of that. So if you look here, we're given a diagram, and in this diagram, there in the middle you see there's a circle. There's a circle with a dot in it, right in the middle. And we've said that it means that in this case there, the current is out of the page because you're seeing a dot. And if you use our right hand rule, you say, okay, if it's out of the page, it means it's moving towards you. You're only seeing that dot. Think about that example that we've spoken about. So you're seeing the dot and it's coming towards you, and your hands are curled in the counterclockwise direction. You see, this is how your hands are curled, meaning your magnetic field is moving in this counterclockwise direction. So your current is out of the page and your hands are curled in the counterclockwise or anti-clockwise direction. This is how this would then be the direction of your magnetic field, right? Let's look at a different scenario where in this scenario here you see it's an X. You said that circle with an X means that the current is into the page, so it's moving away from you. That is moving away from you, and what you will be seeing is the back part of it that looks like an X, right? So my highlighter there, X, is maybe a current conducting wire. So you have it's going into the page, and then my magnetic field is moving in the clockwise direction. It's moving in this direction, right? So we show an arrow that it's moving in that direction. So it's moving in the clockwise direction. I hope that is clear. We can expand this further and say, okay, let's look at an example of a circuit. You have the positive terminal, the negative terminal, and there's your conducting wire, and there is your light bulb. So there's current flowing in this circuit because the circuit is closed. And we said if there's current flowing in a wire or conducting wire, there will definitely be a magnetic field, right? Now we want to determine the magnetic fields here separately, here, 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 because you see the direction of the current is different. So we'd look at all of those 4 cases, right? Starting here, and we'll end up here at the bottom. So let us do that. So in the first instances, the current is moving upwards, right? It's moving upwards, and we use the right hand rule. So you hold maybe a pen, and that will act as your conducting wire, for example, and then you'll say, okay, the thumb will point in the direction of the current, so you see it's going up, and the magnetic field will be held in this counterclockwise direction. So you see I've drawn an arrow there to show that it's moving in the counterclockwise direction. Let's forget about the circles there, just the image that I found. The important thing is for you to show the direction. So you can draw more arrows there to show that it's moving in the counterclockwise direction. And you see in that between this plane that is going up and this plane, this horizontal plane, the angle there is 90 degrees because they are perpendicular. The magnetic field produced is always perpendicular to the direction of the current, right? I hope that is clear. Use your right hand. Check in which direction are your fingers curled. So they are curled in this counterclockwise direction, right? And this will be your current here. Hope that is clear. So let us now look at another example. So now in the second part where your current is moving from the right to the left, right? So there is your current, it's going this way. You take your same right hand, you hold it, and you see that your thumb is pointing in the direction of the current, and your fingers, your other 4 fingers are just curling towards the direction of your magnetic field lines, right? And there you are. So you see that it disappears here and then appears on the other side. So in this direction it's going up, and then it disappears there at the back. So that's the direction of your magnetic field. It's like that, right? Look at an example. In this example, your current is moving downwards, right? This is the direction of the current down. You use your thumb to show the direction of the current in your conducting wire, right? And your magnetic field, now you will look at the direction of your curled fingers. So there you are. So that's your magnetic field as they are pointing in that direction, meaning this whole thing is moving in a your magnetic field is moving in a clockwise direction. So you also just show your arrows over there. You see the black arrow showing that it's moving in the clockwise direction. Do the same thing for the part where your current is moving in this direction. So it's coming from left to right? And there is the direction of your current denoted by the thumb, and then your magnetic field lines will be pointed in this way. I know that the drawing looks terrible, but just look here at the schematic, right? So there is your current in this direction, and there is your magnetic field lines pointing in that direction, and they are moving. So it's coming. It's almost like that. I hope that is clear. So very important for you to understand and to use the right hand rule. So the thumb of your right hand points in the direction of the current, and your fingers points in the direction of the magnetic field lines, right? To show that when there's current flowing through a conducting wire, the magnetic field will be produced, right? Another example we can look at, because in the previous cases we've just been looking at a straight wire, right? But now let us look in a case where it forms a sort of a loop, and then we say we have current flowing through that loop. So flowing through that loop, you see that it's going in this counterclockwise or anti-clockwise direction. And we know when there's current flowing through a wire, we will definitely have magnetic field, and that magnetic field will represent it using magnetic field lines, right? So in this case, we want to use a variation of the right hand rule. So in this case, you'll say, okay, let's say my thumb will actually point in the direction of the magnetic field, right? And my curled fingers will point in the direction of the current. You see, so it's pointing in that direction. It's going to form that clockwise, counterclockwise movement, right? Forms that counterclockwise movement. That's my current, and my magnetic field lines will point in this direction. So it's going in the upper direction. Hence, you see that there you draw a line in the middle, showing the magnetic field seems to be pointing upwards. So it means it disappears from this end and appears on the other end. And then as it gets closer to the wire, it curves a little bit, but it still emerges from the top there, and it looks as if it disappears from the bottom. And then if you look at this sketch, it looks similar to how we draw magnetic field lines around a magnet. So we know that magnetic field lines will emerge from the North Pole, right? There you are, and it's almost like emerge, and then there they go, and it's almost like they disappear. This is actually wrong. This should be like this here. So seeing that this sketch is actually a bit misleading now. So it's almost as if they emerge from the North Pole and disappear into the South Pole. So if we look at this, it's almost like we've created a magnet without actually having a magnet. So if we look at this will act as like the North Pole, and because they will disappear at this end, it will act as the South Pole. So you see, just by passing current through a conducting wire, you sort of create a magnet. So remember the flow of current, that current flowing into it, we call that electricity, and it will create a sort of a magnet. Hence we have electromagnetism. But then you can also look, you say, okay, here we have a single loop, this circle here. What if we stack a number of loops together so that we can create a much stronger magnet, right? We can do that. And when we do that, we say that is a solenoid. So you see here we have a number of loops that when we pass current, it means that we'll be creating a much stronger magnet. So that solenoid is a coil of many loops or a cylindrical coil of wire that acts as a magnet when we pass current through. So let's say we passed current and it was moving in that direction. This will be the positive terminal of your battery, maybe the negative terminal, and you pass current through it, you'll actually get a magnetic field around this. So the more the number of coils, the stronger your magnet, right? So let us look at an example when we talk about a solenoid. So we have a battery over here. Okay, let me fix this before. So we said in a typical magnet, those lines, they move from the North Pole and they seem to disappear here. Don't see the arrows there, they are wrong. I didn't carefully look at them, so they will look like they are disappearing at that end, right? So you have a battery, so this would be the negative terminal of your battery. Over there, this would be the positive terminal of your battery. So your current will be flowing in this direction of the conventional current. Ooh, you see, I'm trying to draw an arrow that is facing up. You see, then it goes here. And then we say when we talk about loops and solenoids, we have to use a variation of the right hand rule. So here my fingers will represent the current. So you see it's in this direction over there. So those will be like my current. So it's moving in that direction, over there. And if it's moving in that direction, it showed my thumb will point to the left. This is to the left, just that it's a bit skewed. Where's my eraser? So my thumb is pointing, where am I? Is pointing in this direction, right? So it means that my magnetic field lines will emerge from this direction. Hence, these arrows over there, you see these arrows are coming out of my solenoid from the left hand side. So this part will act like the north pole, and if they are coming out of there, it means they will disappearing on this end. So this will act like, wait, the south pole. Okay, the south pole, right? So it behaves like a magnet, and the number of if the number of loops increases, the strength of your magnet actually increases. The strength of your magnetism increases the produced magnetism, right? Let us look at the different cases where we change here the battery. So now you see on this side we have the positive terminal, and on this side we have the negative terminal, right? Still using the same right hand rule, the variation of it, where this will point in the direction of the magnetic field lines, and we check how your current flows. So your current will flow from this direction, and it will appear there. You see, so that will be your current there, and then it will point there. The thumb will point in this direction. So meaning this will be your act as a north pole, and this will act as a south pole, and your fingers, your curl fingers, will show the direction of the current. And then here it's fine, but remember these lines, these arrows there are supposed to be in this way. They're supposed to be going towards, not outside of the north pole, the south pole, right? I hope that is clear. Just it's important for you to understand, especially the workings of a solenoid, because in the next video we're gonna talk a lot about it, and for you to be able to use the right hand rule to show the direction of the magnetic field in a straight wire that we did previously, as well as a variation of the right hand rule when we talk about loops, or when we talk about solenoids. I hope that was clear. That actually brings us to the end of this video tutorial. The next video on this, just be on the lookout for it. Still going to be on electromagnetism, where we're going to talk about Faraday's law of electromagnetic inductions, and we'll also do a couple of calculations. Thank you so much for watching.